Hey all, I'm Paul. I am a developer relations engineer with the TensorFlow team. So while my team covers a variety of different ML topics, my main focus is primarily with on-device machine learning, mostly in the Android and IoT space. So historically, this has been TensorFlow Lite for mobile, TensorFlow Lite for microcontrollers when we're working the IoT side of things. But recently, we did announce kind of a newish product called MediaPipe Solutions. So I say newish, it's because MediaPipe already exists as a framework and library that's already out there. We're just building on top of that now to release a couple new things that will make life a little bit easier. So the first part of it is called Tasks, which is basically just making it so you have a lot less code to actually release these different feature sets. And then we have something called Model Maker, which is going to help you make models, and then Studio, which I'll kind of go into a little bit later as well. So overall, my goal is to make it so that you have the vocabulary to look into these tools later on when you actually want to use them, rather than being like, here, you just have to know all of this right now. So you'll be able to go into documentation, understand what's going on, kind of remember some of this, hopefully, and just know that it even exists. So before we start, I did kind of want to cover a few really high-level concepts for machine learning. So while a traditional program is going to take known inputs and a known function to produce an output, machine learning is actually going to take a set of known inputs and known outputs, and then it's going to try to figure out what the function is between the two of them to generate results. So let's say you have one that will add 2 to any number that you give it. So 2 is going to give you 5, 7 will give you 9, 40 will give you 42. So basically with machine learning, what will happen is it will take the inputs, take the rules, or the outputs, and trying to figure out what that is in between them. But basically what this is doing is it is making predictions. So do I have a slide on that? Yeah. So it's not going to give you very deterministic results necessarily. It will make predictions. It's not always going to be 100% accurate. The idea here, though, is that you would want to basically use it as a tool to make better guesses of what you want to do rather than relying it as kind of the definitive, this is what I should be doing based off of what my model said. And then the other part of that is that machine learning is going to allow your apps to do things that are incredibly difficult to do with more traditional programming techniques. So even just a few years ago, it would have been really difficult to find a bird or a diseased plant just off of an image or a video. Whereas now we can actually do that with just a few lines of code, which is one of the things that I want to be able to show with MediaPipe today for Android. So MediaPipe is specifically for on-device machine learning. This means that it's meant for running machine learning inference directly on a device, rather than having to send all that data up to a server somewhere just for processing. So this is actually going to give us 3 major advantages from this single attribute. So we can run inference more quickly since we're cutting out that whole transit time. We can actually use machine learning on the device when the internet is down or unavailable or what have you. So say somebody is on a subway or out in a rural area and they just don't have a signal. You're not going to lose the functionality that your app would be providing just because they don't have that connection. And then privacy is preserved because the data never actually leaves the user's device. So with that, models are kind of the heart of on-device machine learning. So generally you would take a single model, like one for object detection, and bundle it into your program. So this is going to let you customize single options or operations for your purposes. They're generally fairly lightweight. They're not amazing. Some of them are still tens of megs for the models. It's not the best, but it is what it is. But they can be optimized for different device constraints, including memory, computation, power, storage, and all the other fun stuff that is always a trade-off with mobile devices. And then there's ML pipelines. So these are going to streamline the process from your initial raw inputs all the way to your output results. Oh, I lost a screen. It's still good? Okay. So this is going to be your domain-specific pre-processing, such as resizing and rotating images, end-to-end pipeline acceleration for improving performance on your models, and then ways to deploy those models across multiple platforms, including Android, iOS, web, and all that fun stuff, which itself is kind of complicated just to make it work across different platforms. So the problem here is that regardless of whether you're using a model by itself or an ML pipeline, you're still going to require some general machine learning and domain knowledge, as well as putting some effort into designing, building, and optimizing your features. So this gets complex, and it's kind of one of the biggest challenges that we've seen from developers when they're trying to add ML features into their apps. The problem with this is that because of that extra effort, it's less time that people are able to put into coming up with really cool features for their own web, mobile, and IoT applications, where what we're trying to do is have this MediaPipe addition to make it a lot easier by abstracting a lot of the complexity away with a tool called MediaPipe Tasks, which is going to handle a lot of flow control, pre and post processing, and synchronization steps on top of the inference that we're already handling with TensorFlow Lite. So in addition to Task, I kind of alluded to this earlier, but we have another tool called MediaPipe Model Maker, which is kind of the next iteration based off of TensorFlow Model Maker. So this will help developers create their own models based off of their own sets of data and whatnot that they already have available using existing templates. Plus it allows you to do customization and improve performance and whatnot if you want to get into that kind of granular level of things. So while the original Model Maker can only output a single TF Lite file for single task, MediaPipe Model Maker will also allow developers to essentially chain multiple tasks together to create these new tasks files. And then we have MediaPipe Studio, which is the last thing that I was going to kind of mention before we really get into code and all that fun stuff. This is going to include a web tool that will let you test out specific tasks and models directly in the web, rather than having to create a new tool to even like make sure your model does kind of what you think it's going to do. And then one of the things we're working on right now as well with that is the ability to train a model by just giving it essentially a zip file of data and then telling it to make a new gesture recognition one or a new object detection without any like extra customization and whatnot that goes with it. So yeah, before I really dig into how this all works with Android though, I did want to kind of point out too that one of the big points that we're making with this is that it's going to work across multiple platforms with the same feature sets. So right now everything is actually written in C++, and then we're releasing APIs on top of that so that we can use it with Android Web and Python. And then we're working on iOS right now that should be in preview hopefully in the next few months or so. So on top of that, with a combination of the individual models and the combined task, we're actually aiming to support about 20 different ML features by the end of 2023. So right now the focus is primarily on natural language processing and vision, though there is some audio ML support as well right now, and then we have this other section called like more or other. That's going to include things like recommendation, speech, and tabular classification. We haven't really fleshed it out a ton yet, but that's going to be kind of our catch-all for anything that doesn't fit in these three main categories. So as of today, we actually have 9 different tasks that are ready to go right now. You can actually go and make a sample app with them or whatever you want to do. So we have audio classification, embedding. I'll actually end up talking about audio classification, image classification, object detection, gesture recognition, and text embedding just today. So that'd be kind of cool. Yeah.
Do we ask questions?
Oh yeah, I don't care. Go for it.
So this MediaPipe, is that mostly for model training on the device or is for inference?
Inference.
Oh, it's way, so
Yeah.
training is in Vertex AI, and you deploy the edge model like a stream, like
So the
model.
the training will be with your model maker. Just like you would do with TensorFlow or any of that kind of thing, or you can just use Python by itself and then convert it over from normal TensorFlow. But yeah, once you have that actual model file, you'll put that in your assets folder and then be able to run the inference locally.
I see.
Yep.
Would it accept the saved model format from Vertex AI custom model training?
From
Vertex AI is part of Google Cloud.
I don't know. I've not played with Vertex enough.
No.
Oh.
So let me just clarify. Like Paul said, this is mostly for inference. However, the model maker, MediaPipe model maker, or previously known as TensorFlow Lite model maker, is for using the transfer learning and putting some images, and it will make a model for you. But the purpose is not like if you use another pipeline or train on your own, you have a safe model. It's not like that. But you either use model maker or you just like convert it to a TF-Lite model.
Oh, so it has to be converted to a TF-Lite model?
Yeah.
Yes.
Oh,
Yep.
yeah. I
Yep.
think from saved model format, there's a way to convert to
Yes.
TF-Lite.
Oh, yeah.
TF-Lite can do that.
Yep. And then we have tasks too, which are going to support some of the other things that TF Lite couldn't, like gesture recognition. I'll kind of explain that in a bit too. That it consists of like 3 different models to make gesture recognition happen. So we have another tool that will take TF Lite models and combine them and make it a thing as well.
Oh, okay.
So cool. Yeah, so I was going to kind of start with image classification. It's kind of the hello world of machine learning, so it's kind of fun to look at too. So for example, with a single label classification model, this image of a cat will likely just say cat because it's the most prominent thing within the image. Whereas if we have a model that supports multiple labels, then you'll probably have cat, rug, and toy as all potential items just because they are able to be seen like within the image. So I did want to kind of take a quick look at just how classification works on a conceptual level before I even get into like all the code aspects that go with it. So this is all working with a convolutional neural network, and the main way that this tool is going to approach things is by looking for patterns in images during training. And then it's going to try to find those same patterns in new images. And this is the super simplified version of it because I don't know a ton of detail. But kind of getting back to that cat image, if we say that we have thousands of cat pictures on your phone, which no one that has a cat does, you could take all of those and use it to train a model so it can look for patterns like ear shape, eye shape, and ear shape. And then once it has those patterns kind of figured out, it can try to find them on another image that it hasn't seen before to hopefully, at least with some level of confidence, determine that, hey, this is also a cat based off of these patterns, as long as it has some or all of them or so forth. And then the next thing to know is that classification happens across multiple layers of an image. So for example, Android may provide an ARGB image, but since the alpha layer doesn't actually give us much information, we can just go ahead and drop that. But then the rest of the colors are looked at to try to essentially perform classification by finding various patterns across the different layers based off of colors and what have you. And then finally, images do need to go through another step called few pre-classification steps to deal with scaling, shaping, and rotating, just to match the image parameters that the model was trained for to make life easier. So for example, a model may have shrunk images to 32 pixels by 32 pixels. So your Android app will need to do the same to perform classification, and this is your pre-processing step. So here you can see a kind of quick example of a multiple label classification app working in Android. The sample is actually online as well, so you can read all the code on all that fun stuff. So for this graphic, I'm just importing images from the camera gallery and then doing the classification on that. And then out of curiosity, does anyone recognize where these images are from? No, it's the Seattle Aquarium. I just grabbed them when I was touristing about. Cool, so the very first thing you want to do is import the MediaPipe dependency that is going to make sense for your app. So for this version, I'm bringing in task vision, but we also have task audio and task text, just depending on which subset you're working with. And then the next thing to do is create the actual object that will do the classification for you. So this pattern is going to be pretty similar through all of the examples, so I'm going to kind of just take a second to go through it now so we can hand wave it away a little bit as we go forward. So there's two levels of options that will be combined to create the classifier. The first is the base options, which is where we're going to create this essentially with a builder pattern. And then one of the properties that we can associate with that base options is the delegate. So delegates basically are going to determine what hardware should be used for inference. So currently, MediaPipe Task is going to support the CPU, which is slower, but most devices have one, all devices. And then the GPU, which is faster, but it may not be supported by a given model or a given device. So for these next two lines, we're actually going to set the path of our TF Lite model and then create the base options object. For image classification, you would use a TF Lite file because it's just a single model task. If you're doing something like gesture recognition, which we'll talk about in a little bit, it's going to use a .task. So this is essentially just saying, hey, here is my model file, here's where it exists. Like I mentioned earlier too, this is all going to exist within the assets folder, so it does need to have the model placed on the device. Either at build time, you can put it in there and then just compile it into your APK, or you can download it and store it for access later on. And then the next block is where you need to create the image classifier options. They're going to be used for creating the image classifier. So we have this two set of options that you kind of sequentially do. So this is where we're going to set the score threshold, which is essentially how confident is the model in what it's looking at for results. And like, say it has to be 80% confident before you get to those results, because you're only interested in it being very confident type of deal. You can also give it the max results that you're expecting back. So it can give you 0, it could give you 5 if you set it to 5, that sort of thing. And then you have the running mode. So the running mode that we're using here could either be for still images, video files, or live streams. So in this case, I actually think I'm using it for live streams because I was going to go off of the camera feed for it. And then the last step is just to actually go ahead and associate the first set of options with this set. So the base options are the ones that are going to be across pretty much any model and task in that set. And then the image classifier ones are going to be particular to image classifier options. And then because this is for a live stream, you do have to have these result listeners and error listeners to be able to get the results back, because anything that's working with a live stream is going to be working asynchronously. So these listeners will be associated with the classifier to get those results back to you. And then finally, you can create the new options and use them to create the new image classifier object that's going to handle all of the majority of the work, all the major parts of the work. Cool. So as for getting the images to the image classifier, I'm not going to get too much into the details, but our vision samples are using camera X to retrieve camera frames, and then we create an image analyzer to process those frames. So for this example, our model is actually expecting RGBA 8888 formatted images in a 4:3 ratio from the camera, because the model itself is trained for 320 by 320 pixel images, which are square. So 4:3 is at least close enough, and then with the RGBA format, it's easy enough to actually do all the classification with it. Once each frame has been pre-processed, though, we can just go ahead and send that to another function, which is going to do all the classification for us. So that function is going to take the image proxy object that was created for the analyzer, and it's just going to go ahead and turn it into a bitmap buffer. And then from there, we're just going to want to make sure that the image is rotated to be aligned with what the model expects, and then create a new MediaPipe image that gets classified using the classify async method. So one of the big things about MediaPipe too is that it is supposed to do the pre-processing and stuff for you. We're still in preview. You can pretty much ignore this slide later on. It'll be cleaned up and just kind of do a lot of that for you out of the box. But right now, this is what you would need to do if you wanted to take the sample and just make it work. Let's see. So that is pretty much how you would do image classification for a camera frame. It's honestly the more difficult option because cameras are notoriously awful on Android. It's up there with Bluetooth for being like terrible. But if you want to classify a single image, then you can just go ahead and pass the bitmap into the bitmap image builder to create another MP image object, and then call classify on that to synchronously get your results, and then do whatever you're going to do with them elsewhere in your app. Cool. So at the end of all that, you should be able to classify items through your device camera, kind of similar to what you see on the screen here. So the next thing I want to talk about is object detection. Since the code implementation is really similar to image classification, I'm going to just go ahead and focus on theory for this part. So not only does an object detection model help you classify objects, but it helps you find out where they are based on the input. So what's interesting about object detection is that it's actually made up of 3 separate functions that give you the end result. The first is what we would traditionally call detection, whereas the model is going to try to determine if an object that it's trained for even exists within its view. Generally, this is going to happen through statistical analysis. And then once it actually determines that something does exist that it's looking for, it's going to try to classify it just like we did with image classification to give it its title and confidence. And then the final step is called localization. So this is the process where the model is going to try to determine where it thinks that object is within the image or the frame. So the real tricky part for object detection is that the inputs are rarely uniform or really perfectly matched up to the training data. So you may have 2 separate objects that the model is trained for, but one is going to overlap with the other, and then that'll give you a false negative on the second object. You might also have an object that is just kind of in a different orientation or different size compared to what it was trained for. And finally, you might have something where, kind of similar to overlap, where an object might be partially within frame and partially within, like without of it. Basically addressing all of these are kind of outside of the scope of this talk because it's more on the training side, but as Android developers, it's always good just to know where things might break so you can go talk to people and kind of work through the problems later on. And then to wrap up the last kind of interesting vision example, I was going to go over how we would do support for gesture recognition. So here you can see that I'm doing a thumbs up, thumbs down, closed fist, and open palm with a pre-trained model. Similar to object detection, gesture recognition works through 3 separate steps. However, each of these steps are actually made up of their own model, which are trained together in their own pipeline. So the first model is going to attempt to detect the presence of a hand, just to make sure it's even there, before it moves on to the next phase. Then that phase will attempt to locate useful landmarks like each of the knuckles, fingertips, base of the palm, that sort of thing. And then the very last part of this is going to actually try to do the classification on that gesture once it understands that the hand's there and where its landmarks are. Let's see, there we go. So while everything else should be pretty similar to the other vision task, there are some additional options that are kind of interesting to see on this too. So particularly for gesture recognition and also hand landmarks, which is another model that we support, it will want to know what is the minimum confidence it has that there's even a hand to detect a gesture on, how confident is it it's even there, and then like some tracking and some other fun stuff. just because hands are a little bit more dynamic than a lot of other use cases. And then while I've talked a bit about MediaPipe Task, I did want to kind of go back to Model Maker for a second, even though Task are really what's most relevant to Android developers. So let's say that you wanted to go ahead and train a model for sign language. Although we currently have the one that's like closed fist, thumbs up, thumbs down, all that good stuff, if you have enough images for other static gestures, you could use the MediaPipe Model Maker project tool that we currently have to basically retrain one for these. What's tricky about this too is right now there's talk of getting this working with dynamic things. So like with sign language, it's never always going to be just static gestures with letters and whatnot. Like let's say you want to use the word face. You move your hand like this in front of your face. You want to know what gesture is the hand making? Where is it in relation to the face? How is it moving? There's a lot of other things that you'd want to put into this pipeline. In progress. But that'll be a whole other problem to solve later on. But if you are interested in training something for just static gestures that are new, we have a link here. This is a collab that I've already put together where we have provided some kind of staple data that you'd be able to use. Yeah, actually, I'm kind of ahead on time. Let me see if I can show you. I'd pull this up too. Maybe it will work. Yeah. So if you want to go through this, it basically goes you through the whole process of importing just a general image, doing all the training on it, bringing in MediaPipe Model Maker, reclassifying, storing all that data, and it gets you to the point where you're actually able to do the classification for rock, paper, scissors based off of an image that I just kind of already uploaded and then retraining that model. Let's see. There we go. So anyway, this is one that I had already retrained to do rock, paper, scissors. So you can now see that it's going from the like victory sign now, it just shows us scissors, but now instead of fist closed, it's rock. Thumbs up and thumbs down don't actually come up as anything. They're just none because the old values that it was trained for are stripped away for rock, paper, scissors. And this is actually one that I made using that collab that I just showed. So you'd be able to go through this whole process, just swap out the task file and do your next thing. Cool, so the next thing that I was going to talk about is audio. So to keep things simple, I'm going to just kind of focus on audio classification, since it's honestly the most common use case that we do see with our developers. So there's a few different ways to represent audio data in a visual way. The first is a waveform, which you can just see here. This represents sound pressure, which is essentially volume, but it's a technical term for it. It's essentially understanding change in pressure and air based off of ambient by sound. It's a whole thing. Volume over a period of time. But this doesn't really give us a full picture of like what's going on because one sound may look very similar to another. So let's say you had a trumpet and a car horn. They might look very similar in terms of a waveform, even though they're very different sounds. So the next option to discuss is the Mel spectrogram. So not only does this measure time against sound pressure, but it also tracks frequencies. So this will allow you to pick out individual sounds with a bit more ease. So when you're looking at a spectrogram, you can just remember that the x-axis is time, the y-axis is the frequency, and then the color is essentially volume. So to give you an idea, both the spectrogram image here and the waveform on the last slide are just me saying hello, and you can kind of see how they match up and the way they actually represent both the same exact audio file. So with the spectrogram, you can actually see how the O is a bit more pronounced and drawn out compared to the rest of the word as well. So with that in mind, I did grab a little video of a tool that we have for spectrograms. This is just a harp, kind of playing descending notes, and you can see how they'll light up as the notes kind of go down over time. So you can see as it goes down, the red and points and whatnot kind of move down with it. Where it's still time, it's still got the volume based off of the shape of it, but yeah. So, and then in this video, I actually set up a live stream of me talking where I was just saying the word right. So once the word, this word actually has a break in the middle of it, which is kind of cool too. So you can see the initial right followed by that kind of like sharp t sound. So it'll be right. And you kind of get that pattern each time with the word too. So it's not just, I don't know, you can kind of see how each word is going to have kind of a similar picture to it. So yeah, what's kind of cool about that too is that word, right, if multiple people said it, different people, it would still have kind of a very similar pattern to it. So what happens with this is with audio, once you actually have it in this kind of a format, a lot of the machine learning concepts that apply to images are also going to apply to audio classification, just because of the way you're able to represent the data. Let's see, so anyway. Oh yeah, so the way audio is actually going to work for this too, especially for a live stream, is that it's going to take that whole stream and it's going to break it into chunks. So here we could say that we have 1 second chunks, and they're each going through. So this would be 4 seconds, the same word coming in, time after time after time. But as you can see with the first instance of speaking that word, right, it's kind of split right down the middle of it. So you only get the first part of it for one segment, the second part of it for the second segment, whereas if you look at the fourth one, the whole word is in there, so that one will classify really well. So the way you can address this is through something called overlap. So basically the input audio is stored in a buffer that's going to be continuously filled with the latest audio, and then it gets rid of that old data at a consistent rate. So if we have a set of 1 second clips that we're analyzing in order to match our model, but then we add in a second set of inference that's just kind of offset by half a second, then we can end up with overlapping about half that data, giving us some more opportunities to actually find audio for classification as it's going through that stream. So say if we look at the one that's on the very left there again, that was split between that middle line, you can now see that it falls perfectly in between those two orange lines, which is the overlap version of this inference. So that one would actually determine or detect as the word that was spoken, rather than being kind of half confident because it only saw so much of it. So to use audio classification in your own apps, you'll start by just importing the necessary library file again into your build.gradle. So this one is the task audio compared to the vision one that we used earlier. And then I'm going to kind of skip over some of this part here. Yeah, we don't need to know all the extra options and all that because we already saw it. So where this starts to vary is that you do need to have an audio recorder, which I guess is going to be responsible for recording the audio device. This is going to need the sampling rate passed to it, the channel configuration, and the buffer size for storing audio data. Then there's also some implementation details that are kind of hidden in here, such as it's using PCM, which is pulse code modulation, which is kind of a subset of wave. It used to be with TensorFlow task library, you had to give it all that information. We've kind of hidden some of that you can overwrite now, but you don't have to worry about the details so much. And then for the buffer size, for storing different audio data, I'm actually using the sampling rate for the expected input length, which for this model is actually 0.975 seconds. Then I'm multiplying that by the size of a byte, and then doubling it so that there's enough room for overlapping and processing before moving on to the next chunk. And then the next step's a little bland, but it's a runnable that gets passes all the information once classification is ready. And then elsewhere in the code, you can just start your recording and then figure out how often classification should run on an executor along with the amount of overlap. So here I'm just using a static 0.25% for a quarter overlap, but the example images from a few slides ago would have used 0.5 for 50%. I don't have a laser pointer, but you can kind of see it's that overlap times 0.25. And then from the runnable 2 slides ago, you can actually extract audio data from the passed-in recording, then call the MediaPipe's classify async method to do the real classification that will be returned to the listeners. So if everything goes well, which who knows, you should be able to consistently record audio on a device and then classify it based off the model that we're using. So in this case, I'm just using YamNet, which has 500 different categories that it can recognize, like the music that you see in this example. So the final thing to go over is natural language processing, which is essentially just how you would work with text inside of your apps. So in this example, you can see text classification happening, where some entered text is classified by how likely it is to either be positive or negative. So while I'm not going to go into a ton about natural language processing and how it works, we actually have a whole video series up on the TensorFlow YouTube channel that's going to cover a lot of the background behind this. So for what we're working with, though, the most important part is that letters or words are matched up to numerical values through a process called tokenization. And then those tokens are assigned a weight towards a classification, such as positive or negative, to match the earlier example that we had. So to do this yourself on Android, you just need to import the MediaPipe Task text task dependency. And then from there, you can do the same sort of options building that we've seen in the other examples, plus creating the actual text classifier object. And then finally, you just need to, since there's no live data, it's basically just going to be passing in the text that you want, calling classifying on it, and getting the results. So you don't have to worry about all the asynchronous stuff and all that fun thing, because there's no live stream data is for audio or video or that kind of thing. Cool, so super easy. It's ridiculously easy compared to the other two, which is kind of nice. So before we move on from natural language processing, though, I did want to talk about how you can use something called text embedding to figure out how similar two sentences are from one another, since it's a little bit more of an interesting problem, I think, than the classification stuff. So this works through a technique called cosine similarities. So the technical way of describing the cosine similarities is that it's going to measure the cosine of an angle between two vectors based on the words that are used in multiple dimensions. So anyway, basically what that means is you can take two sentences that you want to compare and then turn each of those tokens into an axis, and then you can count each of those tokens per block of text that we're submitting to create a vector based on words and their frequencies. Essentially, this is going to give you the slope and the magnitude, which is really the definition of a vector. And then once you have the two vectors representing the sentences, you can just go ahead and measure the angle between them and then take the cosine of that to figure out what the value should be. So this can range from -1 to 1, where -1 is completely unlike, and 1 is the exact same sentence. So for this example, hey world and hello world are going to have an angle of 40 degrees between them, which is going to give us a cosine similarity value of 0.77. So just like the other two examples, you will start by creating all the options and all that fun stuff, and then creating the text embedder object. And then after all that's done, you just take the two strings for the two sentences that you want to compare and then turn them into embed objects. And then you can just call the cosine similarity function to return that similarity value, which is your -1 to 1. And then that is it from the coding side of that, which is cool. So we're actually able to hide a lot of the stuff that's going on with that under just two function calls. So basically this is exactly how text embedding looks on a sample app, where I'm just giving it two quick sentences, hey world, hello world, clicking similarities, and then getting that 0.77 to tell us that they are mostly close. This is something you'd mainly use for a text searcher. It's kind of the big case where you would see text embedding and whatnot coming into use. That's a whole other discussion. So before we kind of sign off with all this, that's kind of what we have right now, but there's a lot of cooler things coming out that I just kind of wanted to mention, since we're taking a lot of the legacy solutions and updating them and then adding on extra things as well. So the first cool thing to go over is face landmarks. So the default model here is estimating 468 3D face landmarks in real time from a single camera, and then basically just being able to track them on the face. So with this piping, you're actually going to be able to use a face transform to make augmented reality applications even easier to do. So here you can see oh hey, they add glasses, or they have a face mesh, all that kind of good stuff. And similar to hand and gesture recognition, the pipeline is going to consist of multiple models that are going to work together. So you're still going to have your detector that operates on the full image, one that's going to compute the face location, and then 3D face landmarks based off of that other information. Let's see. Cool. And then we are working on pose detection and classification. This one actually has 33 landmarks, which is kind of nice too. So this is going to fall kind of under your holistic landmarking examples, rather than the 400 and whatever that we had on faces. So this is going to help you with actually detecting poses, classifying them. It actually works as you move around them as well, by determining where they are and kind of figuring out how that's going to work in three-dimensional space. Yeah. And then the last big thing that I wanted to bring up too is that we are working on optical character recognition. So this is essentially how you would read in text into your app to do any kind of natural language processing on it. So if you use the Google Lens app to kind of read your menus or translate whenever you're anywhere, same exact idea as that, except you'd be able to add it into your own apps as you move forward. Cool. So there's a lot more features that we're working on. Like I said, I think we were aiming for, 23, something like that by the end of this year. This is our GitHub sample repo, this Google samples / MediaPipe one, specifically for Android. All the ones we already have are already up there. We also have a code pen set up for all the web versions of these. So if you want to go in and just try the web ones without having to build anything out, you just kind of click the button with code pen and it's just there, which is kind of nice. If you want to keep up to date, we do have our documentation up on developers.google.com, and then we have a mailing list for all of our announcements as we come out with new features and new everything, essentially. It's still on preview, so everything is still very new and coming through. And then we have an email there too if you want to send us bugs or questions or any of that sort of thing as well. We're at MediaPipe Solutions Team Support. Yeah, that's what I've got. There is my email if you want to reach out to me there. There's also my LinkedIn. We can connect, you can ask me questions, all that kind of fun stuff as well. Cool. And if there were questions or, yep.
So you introduced both the API and the library to use with it. The library, is that something that's developed by that team in-house, like by themselves, or taken from elsewhere? And going forward, is that library sort of the one for Google, or is that one potentially many?
I'm sorry, I don't quite.
So for the library that you were introducing, is that something done by your team?
Yes. Yeah, so it's Google is actually making the library and releasing it for use.
Is it going to be sort of the library going forward for Google, or one of many?
It will be the one for on-device machine learning. So like right now we have TensorFlow Lite task. We're kind of moving it into this. So it'll be just for the inference on-device part of it.
About this chart is the overview of the
That is part of the legacy one.
Oh, that's the old one?
Yeah, that's the older one. We're upgrading that right now.
Oh, okay. Maybe this question may apply. The existing model, do I as a user have to supply that?
We actually have a whole selection of them that you'd be able to pick as kind of our off-the-shelf recommended ones for just the base part of it. And then if you want to customize it, that's where that model maker part would come in, where you use transfer learning to like retrain it with your own data.
So is the retraining process on the device, or
The retraining would be done on like Colab or your own computer, back end side of it. And then you would just take that model file and put it into the app.
Oh, I need to deploy the model to the
Yeah.
device?
Yep.
I see. When I deploy the model, when I customize the model, do I need to specify the processor SoC type like Snapdragon versus Google's Pixel
Nope.
6 or 7?
A lot of that is all going to be pretty much abstracted for you. It'll make the decisions under the for like delegates and all that under the hood.
If I specify the code had GPU and
Yep.
CPU.
So you can tell it to override it if you wanted to.
Was that GPU, CPU? Was that on the PC?
No, that was on the Android app. So like if you have an old Nexus that doesn't have a GPU, you can use the CPU. But if you're using something newer that does have a GPU that's supported, you can switch to that.
Was that line for training or inference?
That was for inference.
Oh, that was for inference.
Yeah, that was for inference.
Okay.
Yeah.
The training is done on the computer.
Yeah, that's all. That's at Colab. I didn't actually really get into the training part of it.
Okay.
Yeah.
I got it.
Cool. Yep.
Great presentation, by the way.
Oh, thank you.
So for text classification, is there a way to attach like a custom dictionary, like for example, clinical terms, for example?
Yeah, yeah. So when you're actually doing your own training, that would be again going back to that model maker part where you have, hey, here is my CSV file of words and tokens and the weight we want to give them. You would train it there, and then once you get that TF Lite file, that's what you would put in your app to do all the custom text classification aspect of it. Cool. And I saw a hand. Yep.
Are you logging the performance logs on the device as well as position and feedback from the actual user? How many predictions are?
I don't think they are, but I can find out. I haven't actually dug into that too terribly much.
Is there anything I need to configure when I train the model? Like if I have a NVIDIA GeForce like 3080, when I train the model, is there a way to make it train faster, or does it even matter?
I don't quite understand that.
Like you said, training is done on the PC, right?
Uh-huh.
Computer. Is he using the NVIDIA GPU or just the
It-
Intel AMD CPU?
It just depends on what you're. So like with the Colab, you can actually tell it, hey, I want to use a TPU, a GPU, what have you.
Okay.
So it's all going to depend on there.
Oh, just what a single Python line change.
Yeah.
CPU, GPU.
Yep.
Oh, okay.
Cool. Yep.
Is there any restrictions in types of layers that we can use with MediaPipe? Like for example, can you use layers like batch normalization or transformers for image models?
So I don't really know on that side. My main focus is on the inference side of it rather than the model training. So it depends on what is even supported by TF Lite for model training right now. So yeah, I don't have a good answer for you on that one.
So I was actually wondering, like, if there's a model with those layers, would it be kind of converted into just like file and be deployed on the same data?
Gotcha. Yeah, I mean, if you can get it into a TF Lite file, that conversion process, I think it does check for whatever operations it would support. So it would probably be okay if you can get it to that stage. I just don't know where all that intermediate is. Cool. Think we're all good? Cool.